All right, so the next group we'll take a look at is the group 13. Or we'll just call these the group 3A elements, right? So this would be now, we're looking at this group here in yellow. Again, main group elements. So this would include boron, aluminum, gallium, indium, thallium, etc. These all have 3 valence electrons. Okay, coming from the NS2 and the NP1, that's where those 3 electrons come from. The first element, boron, is a metalloid. All the others are going to be metals, right? So boron here, metalloid. All the other ones, aluminum and below, are all metals. Boron itself does not form a binary ionic compound, and it's fairly unreactive towards water and also oxygen. Once we get down to aluminum, though, that readily forms aluminum oxide when exposed to the air. So for instance, aluminum can react with O2 to form Al2O3, and that's actually a good thing because what happens is if you have an aluminum sheet or a piece of aluminum on a, maybe on a car or even on a plane, this aluminum oxide forms a very protective coating. Okay, and it's very dull compared to the shiny aluminum. So that protective coating actually prevents further reaction of the underlying aluminum. So it actually extends the life of the of that sample of aluminum, right? So it does prevent further reaction of the metal. So we can actually use aluminum for structural purposes, for structural magnesiums. I'm sorry, for structural materials, aluminum siding, for example, or in the, the shells or the fuselages of airplanes. Aluminum also can form the aluminum 3+ ion. And again, why would it form 3+? Well, because it's got those 3 valence electrons to lose, and it can readily lose those. Other elements in group 3A, they can form the +3. They can also form the +1 ions. So they can do either depending on what it is that they are combining with. Okay, so the group 14 elements are next. And again, group 14 then would be the group 4A. So this would be the group that starts with carbon, and then silicon, germanium, tin, lead, etc. That's group 4A. Carbon is a non-metal in that group. The next two, silicon and germanium, those are metalloids, and the ones underneath, those are going to be metals. So these actually form, or they can form both +2 and +4 ions. And for carbon and for silicon, the first two, the +4 oxidation state is actually more stable. Okay, so for carbon and silicon, the +4 is more stable than the +2 oxidation state. So the last two, so elements in that group, tin and lead, for instance, so Sn and Pb, they are metals, obviously. They don't react with water, so they're fairly unreactive. But they can react with acid to produce hydrogen gas. And they can react with aqueous acids to produce H2. So for instance, if you have something like tin that can react with an acid that gives us the H+ to form tin with a 2+ charge, and then we also get hydrogen gas being really similar to some of the other reactions we saw previously. The next group, the group 15, which will be the group 5A elements, these have 5 valence electrons. Okay, and that would be the group that contains nitrogen and phosphorus, arsenic, antimony, bismuth, scobium. Those are all in group 5A. The first two elements there, nitrogen and phosphorus, those are non-metals. We also have metalloids underneath them, arsenic and antimony. And under those, we have some metals, bismuth and below. So we have all three categories in group 5A. Metals, metalloids, metals, metalloids, and also non-metals. So all three categories are here. As we know by now, elemental nitrogen, right, exists as N2, diatomic, and it can form a variety of oxides. It reacts with oxygen. So, for example, it can form NO, nitrogen monoxide. It can form N2O, dinitrogen monoxide. It can form NO2, nitrogen dioxide, and so on and so forth. And all of those are gases, with the exception of one that we didn't list. Nitrogen has the tendency to not to lose electrons, but to gain electrons. It can form the N with a 3- charge. Okay, so it accepts, gains electrons like typical nonmetals do. And it can form ionic compounds as a result of that with metals, things that want to give up electrons. Phosphorus itself, so P on the other hand, exists as P4 molecules, which is unusual, but that's the way that it exists. So it's white phosphorus, or it can exist as chains of P4 molecules, which is red phosphorus. Right, so white or red phosphorus is typically how it exists. It can form two solid oxides. You can form PO4. It can also form P4O, I'm sorry, P4O6, or it can form P4O10. So these can form oxides as well. For example, those two. And then the oxides can react with water to form acids. Okay, and some of these acids are very, very important. They're used on industrial scale, so huge amounts are used typically. So for example, an oxide of nitrogen, such as N2O5, dinitrogen pentoxide, can react with water to produce nitric acid, HNO3. You can have oxides of phosphorus, such as tetraphosphorus decoxide, P4O10. That can react with water to produce the corresponding acid, which would be phosphoric acid, H3, PO4. All right, so the next group that we have is the group 16 elements, which again, this would be the group 6A, right? So these are going to have 6 valence electrons. The first 3 elements are nonmetals, oxygen, sulfur, and selenium. And these are the forms that they exist in naturally. So oxygen is the diatomic, sulfur exists as S8, selenium as Se8 as well. Typically now, because these are nonmetals, they're in group 6, they will tend to accept or gain 2 electrons, and they will form the ion with a 2- charge. So for example, we end up forming O2-, the oxide. We can form the sulfide, S2-. We can form the selenide, Se. 2 minus, etc. So the group 6A elements, they typically form a large number of molecular compounds or covalent compounds with other nonmetals. Okay, so other nonmetals like to combine with these, and there's actually a huge variety of compounds that are created. And some of these are very, very important compounds that have sulfur, for example, or oxygen in them. And just like in the previous example, some of these can be used to create other materials that are used on a huge scale. So for example, an oxide of sulfur, such as sulfur trioxide, SO3, this can react with, we can combine it with water. We end up producing an acid, sulfuric acid, which has a huge, or it's produced on a commercial scale. It's found in battery acid, for instance. The last couple elements are metalloids, so tellurium and polonium. Those are not nonmetals, they're actually are metalloids. Okay, so as we keep going across to the next group, group 17, which would correspond to group 7A. These have 7 valence electrons. This is the halogen group. Okay, these are all diatomic. They exist as diatomic molecules in the natural state. So for instance, we have F2, Cl2, Br2, etc. They do not exist as individual atoms in nature because, again, they want to be as stable as they can be, and they're way more stable in the diatomic form rather than in their individual atomic form. These form halides very easily, right? And halides have 1 minus charge on them. So for instance, fluorine can form the F1 minus, chlorine Cl minus, bromine Br minus, etc. Right? And that's because of their high ionization energies. They don't want to lose electrons, but instead they have large, energetically favorable electron affinities. All right, so it's way more favorable for them to gain that 1 electron than it is to lose any other electrons. They can combine with metals to form ionic compounds. Okay, and we call those salts, right? All a salt is an ionic compound. And your halogens form salts with metals very easily. They can react with each other to form molecular compounds or covalent compounds. As we've seen previously, they can also react with hydrogen to form hydrogen halides. So like down here, hydrogen and iodine can react together to form hydrogen iodide, Hi, and then those can dissolve in water. So this, for instance, can dissolve in H2O to form the general hydrohalic acid. So for example, when Hi dissolves in water, we end up forming the hydroiodic acid. If I had HCl dissolved in water, that would form hydrochloric acid. So the last group on the table, periodic table on the right side, is the group 18, which corresponds to the group 8A elements. These are the noble gases. Okay, they all have 8 valence electrons with the exception of helium, which only has 2. These all occur as monoatomic or monatomic elements. So for instance, we have just He, we have just Ar, just Ne, etc., just Z, Xe. And they're stable, they're unreactive because they have a full valence shell, right, completely filled with electrons, which give them a high degree of stability. All the other elements in the periodic table want to be kind of like them in terms of their stability. So they are unreactive or inert. Inert means unreactive. And generally that was the case until, in the middle of the last century, when xenon and krypton were actually used to make compounds, right? Which is highly unusual because if they're stable, there's no need for them to react. But in some cases, they can under the right circumstance. There really isn't a whole lot of commercial use for these, and definitely there's no biological use for these, so we don't tend to see them very often. But they are important. They form a pretty significant portion of the periodic table.